We want to sketch the graph of the function f of x equals 5x over x squared minus 36. Now this is a rational function because it has a variable in the denominator. I'm going to start with finding the domain of this rational function. With rational functions, we're concerned about the denominator equaling 0. So I'm going to start by setting the denominator x squared minus 36 equal to 0, and I'll solve. I can solve this by factoring. It factors to be x and x, 6 and 6 with a plus and a minus. This is a difference of squares. And then we'll use the zero product property and set each factor equal to 0. I'll subtract 6 on each side to get x equals negative 6, and I'll add 6 on each side to get x equals 6. This gives me the restricted values. These values will cause the denominator to equal 0. Division by 0 is undefined, and so these values have to be excluded from the domain. So I'm going to write my number line, mark negative 6 and positive 6 on that number line, and I'm going to shade everywhere else. All of the other values on this number line, besides negative 6 and 6, are included in the domain. So we want to represent each one of these shaded regions as a part of the domain. And we're going to represent them in interval notation. And interval notation has a lower bound and an upper bound. So this first interval, this arrow indicates it's going on forever. So that first interval starts at negative infinity. It stops at negative 6. We use a parenthesis to indicate that negative 6 is not included in the set. The next interval is negative 6 to 6, and the next interval is 6 to infinity. So this is the domain. The domain of this rational function is negative infinity to negative 6, union with negative 6 to 6, union with 6 to infinity. More simply stated, it's all real numbers except for negative 6 and 6. So now that we found those restricted values of negative 6 and positive 6, I want to figure out what type of restricted value they are, in the sense that we have two options. They can be a hole in the graph, or it can be a vertical asymptote. So I want to figure out which one. In order to determine which one, I want to write my function in factored form. So I'm going to start with that 5x in the numerator. 5x is already factored. And we've seen that we can factor x squared minus 36. It's a difference of squares. X minus 6 times x plus 6. And once we have it in factored form, we're going to look for common factors. So if we have common factors, that's an indication that we have a hole in the graph. And since we don't have any common factors, we have no holes. And what that tells me is that these two restricted values that we have are both going to be vertical asymptotes. Since we don't have any holes in the graph, since there are no common factors, these restricted values of negative 6 and positive 6 are vertical asymptotes. Now that's important in sketching the graph, because that tells us how to draw the graph near these values. So we know because there is a vertical asymptote at x equals negative 6, as x gets close to -6, our y value will approach infinity, or y will approach -infinity. And the same thing goes with +6. Because there's a vertical asymptote at x equals 6, we know the behavior of y near that value. As x gets closer to 6, y will approach infinity, or y will approach -infinity. We'll take a look at that a little bit more as we continue to draw the graph. The next thing that we're interested in is if this function has a horizontal asymptote. In order to determine if it has a horizontal asymptote, we're going to look at the degree of the numerator, which we call n, and the degree of the denominator, which we call m. So what we look for in our function, we look for the power on x. So in the numerator we have 5x, and the power on x is a 1. So the degree of the numerator is 1. In the denominator, we have a power of 2 on x, and then a term with no x. So that means that our degree is 2. We take the higher power. Once we've determined that degree of the numerator and the degree of the denominator, we need to compare them. And there's one of 4 cases that we're hoping this falls into. In fact, we're sure it's going to fall into one of these cases because this covers every possible scenario. So these are the 4 cases that we pay attention to. The first one is n being less than m. The degree of the numerator is smaller than the degree of the denominator. The second case we pay attention to is when the degrees are equal to each other. So the degree of the numerator is equal to the degree of the denominator. The third case is that n is m plus 1. The degree of the numerator is 1 more than the degree of the denominator. And then finally, this is the one that fills in the gap of every other possibility, that n is greater than or equal to m plus 2. So this is saying that the numerator would be larger than the denominator, and it's larger by 2 or more. So looking at our situation, we have n being 1 and m being 2. N is less than m. 1 is less than 2. And so we are dealing with this first case. Now, once we know we're dealing with the first case, we have memorized a set of rules for each one of these cases. Now, the reason why we're memorizing these rules is because the actual math behind finding the horizontal asymptote involves an operation called the limit, which is a calculus operation that we haven't introduced. So we've summarized these rules so that we don't have to deal with that operation in this algebra class. So the rule that we have memorized is that anytime n is less than m, the degree of the numerator is less than the degree of the denominator, we will have a horizontal asymptote, and that horizontal asymptote occurs on top of the x-axis, which is the line y equals 0. So this function will have a horizontal asymptote at y equals 0 because the degree of the numerator is less than the degree of the denominator. The next thing that we're interested in is determining if our function, if the graph of our function crosses the horizontal asymptote. So to have our graph cross the asymptote, we're going to create this equation where we set the function equal to the horizontal asymptote. That's going to give us 5x over x squared minus 36. That's our function. We want to see if it crosses the asymptote, and that horizontal asymptote is at 0. So if we solve this equation, we're going to find out if the graph ever crosses that asymptote. So to solve this, I would multiply both sides by x squared minus 36. That will eliminate the denominator. So we cancel out that denominator. We're left with 5x on the left. On the right, 0 times anything is 0. And we have this equation 5x equals 0. We'll divide both sides by 5, and we get x equals 0. So because we got a solution here, we do know that the graph will cross the horizontal asymptote at x equals 0, and we can find the y value at 0 because that's where the horizontal asymptote is. So this is the point where the graph crosses the horizontal asymptote, y equals 0. The next thing we're interested in is if this function has any intercepts. So we're going to look for x and y intercepts. So we look for a y-intercept by letting x equal 0. We're going to substitute a 0 into our function. That would give 5 times 0 over 0 squared minus 36. That's 0 over negative 36, which is 0. So the ordered pair 0, 0 is a y-intercept. Then we're going to look for x-intercepts. We find x-intercepts by letting y equal 0. We're using function notation. So f of x is our y. So we're setting f of x equal to 0. That would give us the equation 0 equals 5x over x squared minus 36. That happens to be the same equation that we just solved over here. So we already know the solution to that equation is going to be 0, 0. So we have 0, 0 being an x-intercept. It's also the point where the graph crosses the horizontal asymptote, and it's also the y-intercept. So we've seen that 0, 0 show up in those places. So now I think we're getting closer to sketching the graph. So let me put on the screen here a grid for us to use. We can make that a little bigger. So let's start writing down what we've learned so far. So we have learned that we have vertical asymptotes at x equals -6 and +6. So I'm going to draw a vertical dashed line at x equals 6 and a vertical dashed line at x equals -6. These vertical dashed lines are going to act as guides on how to draw the graph. We also have found that this function has a horizontal asymptote at y equals 0, and that is right on top of the x-axis. Let me label these. We have a vertical asymptote at x equals -6, a vertical asymptote at x equals 6, and a horizontal asymptote at y equals 0. We also have found this ordered pair 0, 0 is a special point. It is the point where the graph crosses the horizontal asymptote, it is also the x-intercept and the y-intercept. So this is all the information I have so far, and I don't feel confident in drawing the lines at this point. What I'm looking for is to have some ordered pairs in every one of these sections that are divided up by the vertical asymptote. I do have one point in this middle section, but that one point is not really enough for me to know how to draw the line. There are just too many choices. I'm not sure if I draw the line going to positive infinity or if I draw the line going to negative infinity. So I need some more information because there's too many choices. And the same thing goes with these outside sections. I don't have any points in this section or this section to help me decide whether to draw the line going to positive infinity or negative infinity, positive infinity or negative infinity. Like I said, too many choices right now, so I need some more information. So what I'm going to do is I'm going to choose some points in each one of these intervals. So I need to pick a value that is less than -6, like -7. In the middle here, I want to pick a number in between -6 and +6. So maybe I'll choose negative. Actually, it might be easier if I choose some, yeah, let's do -5 and +5. And then in this last section, I need to pick a number that's greater than 6, like 7. So I'm going to pick these values for my x's, -7, -5, 5, and 7. We're going to substitute it into our function to get the y value. It's 5 times -7 over -7 squared minus 36. 5 times -7 is -35. -7 squared is 49. 49 minus 36 would be 13. And we're going to get an approximation of that with our calculator. 36 over 13, we get a -2.8. We'll do the same thing with the rest of the values. We have 5 times -5 over -5 squared minus 36. That's -25 over 25 minus 36. 25 minus 36 is -11. And this 25 should be negative. 5 times -5 is -25. So 25 divided by 11, we've got a positive 2.3. We have 5 times 5 over 5 squared minus 36. It's 25 over 25 minus 36. 25 over -11. We have -2.3. Last one, 5 times 7 over 7 squared minus 36. That's 35 over 49 minus 36. 35 over 13 would give me a positive 2.8. So now we have some more ordered pairs, and this will help guide us on drawing the graph. We have -7, -2.8, should be about right here. We have -5 and 2.3, be about here. We have 5 and -2.3, be about here. And 7 and 2.8 would be about here. Now that I have these points, I feel more comfortable drawing the graph. Now, using my asymptotes as guides, remember the definition of our asymptote says that as x is approaching that asymptote, y will approach infinity or negative infinity. And now I know which one to choose based on where my point is. So that point that I plotted is in the negative, so I know that my graph will be approaching negative infinity. And this point is in the positive, so I know the graph will be approaching positive infinity on that side. And we can do the same thing here. This is in the negative, so the y will approach negative infinity. This one's in the positive, so it'll approach positive infinity. In the middle, I can connect these points. Those 3 points get connected, and then the definition of my horizontal asymptote is that as x approaches infinity or x approaches negative infinity, y will be approaching 0. So I know that my graph will start to approach the horizontal asymptote on both ends. And so now we have a sketch of our rational function 5x over x squared minus 36. Thank you for checking out my videos. Have a great day.